In this lecture, we want to discuss the shortest path algorithm. Before discussing the shortest path algorithm, just we will discuss little bit about what is a graph, what is directed graph, what is undirected graph, what is weighted graph, and then we will go to the shortest path algorithm. Basically, if you see we have derived the shortest path using the CPM and part method. Now, we want to derive the shortest path algorithm using the earlier other method, that is graphically. Let us see first the definition. What is a graph? A graph, we say that it is a ordered pair V E, which is a composed of what is V? V is the set of vertices, E is the set of edges connecting the vertices. So, basically a graph will have a set of pairs of the form V E. V is the set of vertices, E is the set of edges which connects the vertices, and an edge what you say, that is E equals V U, which is a pair. So, if you take the example over here, what I have drawn over there, but it would be better if I tell from here. If you are having, say, your vertices A, B, C and D, E, these are the vertices are there. If I have drawn a lines from here A to B, A to C, A to D, and there are D to E, C to B, C to E and B to E. So, what are the vertices here? V set of vertices, vertices will be A, B, C, D and E, what we have written over here. V is A, B, C, D, E and E, and the edges will be the pairs. What are the pairs? From the figure, if you see the pairs, one pair is A B, another pair is A C, other pair is A D. So, A B, A C, A B, A C and A D, this is one side. After that, from B you can write down B C and B E. So, B E and B C, this is another one. From C it is C E and then C E, the other one is D E. If you see on the figure over there, so we have drawn it that F equals V is the vertices, and therefore, A B C D E, A B C D E, these are the vertices, and for that the edges are, one edge is A to B, another edge is A to C, other one is A to D. I have written that. The next one is B to E, that is B to C, B to E. The other thing is D to E and C to E. So, therefore, B C I have not written twice, B C is coming only once. So, if you draw any graph, for the graph there will be a set of vertices and the set of edges like this. The next one is what is directed graph and what is undirected graph. A directed graph is one in which the pair of vertices in edge is it is unordered. It is unordered means undirected graph. Sorry, undirected graph is one in which the pair of vertices in a edge is uncovered. Uncovered means what I have written, that is V 0 comma V 1 should be equals to V 1 comma V 0. That is, if you form any activity from V 0 to V 1, whatever activity time it takes from V 1 to V 0, if you take, it will take the same time. So, undirected means it may be from V 0 to V 1 or from V 1 to V 0. Whereas, just the opposite one is the directed graph. If you see, the directed graph is the edge from where, in this case your V 0 V 1, this should be equals to V 1 not equals to V 1 comma V 0. So, if you have V 0 to V 1 is not equals to V 1 to V 0, that is, there will be only one side edge, one edge, either it will be from V 0 to V 1 or from V 1 to V 0. So, just like whatever I have drawn, that is undirected graph, there is no direction. So, it may be from A to B, from B to A, whereas, if you make anything like this, one arrow like this, then there will be a direction, the direction is A to B. Next, if you see for this one, we have written this is the tail and this is the head. So, basically this I have told earlier also, this is the tail and this will be the head. So, this is your directed and undirected graph. Next is what is weighted graph. We can associate the edges of a graph. Edge, we have told, edges means the directions, the pair A B, edges of a graph with numeric values then the graph we call it as the weighted graph. These numeric values or weights, we say it may be non-negative integers in general, but weight may be a measure of length of a route, the capacity of line, the energy required to move between locations among a route like this. Or in other sense, I want to say that what is the weighted graph? In the weighted graph, if you have you see this figure, to move from A to B, you have to spend either some time, some cost or some labor, whatever it may be, to go from vertex X to vertices B, and that amount may be say 10 units. So, these 10 units whenever you are putting, then we call it as the weighted graph. Like this way I can put weight for each and every graph. So, you see the example, the first one is the weighted undirected graph. You have put the weights, if you see 1 to 2 some weights are given, 8, 2 to 5 weight is 6, like this way the weights are given. So, these are weighted undirected graph, whereas if you see the next figure, then there are directions from 1 to 2, 1 to 4, similarly 4 to 3 like this, and weights are given. So, the next example is for the weighted graphs. Now, we can associate termination, some notations we will use. If V 0, V 1 is an edge of an undirected graph, then you say that V 0 and V 1 are adjacent. Or in other sense, in this figure, if you are drawing A B, you can say A B is adjacent, or this D E, this D E is adjacent. And if this A B is an edge of an directed graph, basically this is I have given a direction. So, A B we are calling is an edge of the directed graph, whereas D E is the edge of one undirected graph. Of course, both cannot occur simultaneously, you have to understand it, that either there will be directed graph or there will be undirected graph. So, if you are having the directed graph, for that if two edges are there A to B, then this V 0 and V 1, this we call as the adjacent. Next is a path is a sequence of vertices V 1, V 2, V k. A path is a sequence of vertices V 1, V 2, V k, such that each vertices V I is adjacent to the next vertices V a I plus 1. So, you are having a path in a sequence, just like if you see A B E D, if you want to go like this A B E D, something like that. For this path, whenever you are moving, it is a sequence of paths moving from here to here, from this position, starting position this, then next position, after that this position, and after this position. If you see, if this is the starting position, next one will be this is, if this is V 0, then this will be V 1, that is if it is V I, it will be V I plus 1, like that way it will be going. You have to note one thing, that in a path each edge can be travelled only once, each edge can be travelled only once, each edge, that is these edges can be travelled only once, and the last one is the length of a path will be the number of edges in that path. That is, if I am moving in the direction of A B E D, then number of edges, this is your edge 1, I am say E 1, E 2 and E 3. The sum of E 1, E 2 and E 3, E 1, E 2 and E 3, the edges which has travelled, sum of these three will give you the length of that particular path. Then the adjacent matrix representation, that is, this graph can be represented in terms of some matrices. So, let G equals V E be a graph with vertices. Usually the adjacent matrix we are denoting, if you see here, we have given it the notation matrix, which is a 2-dimensional array. We have given the notation matrix here. So, if the edge V I comma V j is in E j, then matrix I j equals 1. If there is no such edge, then matrix I j equals 0. Or in other sense, whenever you are writing the matrix, say here matrix I j, whenever you are writing matrix I j, if there is there is one edge between V I and V j, then we say this value is 1. If there is no edge, then we say this is equals to 0. So, the value will be either 1 or 0 depending upon whether for one path I comma j for the vertices v I comma v j, if it is there, then we say matrix I j equals 1, otherwise we say that the matrix I j is 0. The next one is the adjacency matrix for an undirected graph is symmetric, whereas the adjacency matrix for the directed graph may be symmetric, may not be symmetric. For the adjacency matrix for the undirected graph must be symmetric, because there is no direction. And when the graph is weighted, we can let the matrix I j be weight that labels the edge from vertex I to vertex j instead of simply 1. Or in other sense, we want to say, just like if you see this figure, in this figure whenever you are moving from A to B, we have associated one weight, that is 10. So, in that case the value will not be 1, the value will be 10. So, in this case what we are doing, if there is an edge, some value is associated, some weight is associated in the matrix, we put the weights. Let us see the example. In the next example, it will be very clear. For the directed graph, if you see, there is a directed graph 1, 2, 3, 5. So, we have made a matrix. In the matrix, there are 5 rows and 5 rows and 5 columns, because you are having the vertices are 1, 2, 3, 4, 5. So, 1 to 1, if you see, there is no path obviously. So, it is 0. 1 to 2 there is a path, so we have put 1. Similarly, 1 to 3 there is a path, we have put 1. 1 to 4 there is no path, so it is 0. If you see the element of 1 4, similarly the element of 1 5, this is equals 0, and the other rows are coming like this. For the second row 2, only 2 to 4 there is an path from 2 to 4 and 2 to 5. So, these two are 1 and 1 only for the second row. Like this way you are putting the next elements of this. So, therefore, if there is one edge from or path from one vertex to another vertex, corresponding element I j will become 1. If there is no path, the corresponding element will become 0 0. Next one, you see the undirected graph. For the undirected graph also same thing is happening, 1 0, 1 1 is 0, 1 2 3 4, like this way you are doing. The only thing 2 1, if you see here, from 2 to 1 also we have made it 1, because from 1 to 2 there is no direction. So, it may be 1 2, it may be 2 1, both are same. For this reason from 2 to 1 it is 1, and like that way others. This is the only difference between directed and undirected graph, because in directed graph if there is a path from 1 to 2, only 1 to 2 will be 1, whereas for the undirected graph, if there is a path from 1 to 2, then it will be 1 to 2 will be 1, whereas 2 to 1 also will be 1. The other things will remain the same. So, this is the example of undirected graph. Now, the next one is the adjacency matrix weighted graph. If you see, the weights are given for this one. Whenever you are putting the weights, what we have done, if you see 1 to 2, 1 to 1 there is no path, and we have put an cost of infinity, that is an hypothetical value has been assigned infinity instead of 0, because you have some numeric values over here, the weights are non-negative, in general non-negative. So, therefore, we are putting very high value infinity over here when there is no path. So, whenever for the weighted graph, the matrix can be drawn like this. Next one is what is the, so these are the basic preliminaries, you can say that what we require. Then what is the shortest path problem? You already, if you see, you have done the shortest path problem, that is from starting from one node. If you see this node, starting from this node, if I want to come back to this node, how to do it? This basically we are telling that you are having a problem something like this, or it is something like this also, it may be there, say it is like this you have done in the path and CPM. So, this is your starting position, this is your ending position, from this position to this position, in which path should we move so that the cost will be less. Basically, this is your shortest path. So, in an edge weighted graph, the weight of an edge measures the cost of travelling that edge. That is, whenever you are moving from one vertex to another vertex, whatever cost is associated, the cost may be in terms of time, it may be in terms of labor, in terms of money, whatever it may be, that we call it as the weights. For example, in a graph representing the network of airports, the weight cost should represent, it may be distance, it may be cost, or it may be time. Such a graph can be used to answer any one of the following questions. Basically, the same question may be asked in the different way. If you see, then what is the first question? What is the fastest way to move from A to B? What is the fastest way to move from A to B? So, if you see, the next question is, which route from A to B is the least expensive? Which route from A to B is least expensive? And the last one is, what is the shortest possible distance from A to B? So, basically, in which way I should move from one path, one route to A to B, what should be the route to move from A to B such that the cost will be minimum, and what should be that path. So, basic problem is this one. For each of these questions, we have the solution for the shortest path algorithm. A shortest path between two vertices S and T in a network is a directed simple path from S to T with the property that no other such path has lower weight. Please note this one. If you see this one, I want to move from this to this, in between so many things are there. So, whenever I want to move from S to T, then what should be the shortest path, so that I can move from S to T such that there is no other lower weights are available to move from S to T, that is the lowest one. That is, if you see, in a given weighted graph and two vertices u and v, we want to find a path of minimal time weight between u and v. So, minimal time it takes between to move from S to T, that we are calling as the shortest path. And you have to note one thing, that shortest path does not physically represent the shortest distance, but basically the path consists which gives you the minimum weight. Please note this one. It is not that the physically shortest distance, but it will be the minimum weights which you are moving along the path. So, this is the shortest path. Now, what is an shortest path problem? So, your shortest path problem is this one. What are the applications? The applications, if you see, you are writing in map navigation, that means whenever you want to move from one place to another place, we can use this shortest path problem. In circuit wiring, whenever you are drawing the circuits to move from one circuit to another circuit. The vehicle routing, that is, you have to drop some materials at different locations of a city, what path it should follow, for that one. In robots also we use, in VSLI chip optimization this is used, then telemarketing, telemarketer operator scheduling it is used, approximating piecewise linear functions we can use it, network routing protocol also, if you want you can use it. And now, single source shortest path, basically whatever we will discuss, that is the single source and single destination shortest path. So, single source shortest path means I want to say the path starts from a source only, from only one source. If you see, for this problem, if you see, the path may start from here, from here, from here, from here, but and its destination also may be any one of these. But the problem which we want to discuss, basically the problem which we want to discuss here, there will be only one source, that is this one, and there will be one destination, that is this. So, please note that for a given graph G V of E, we want to find out only the shortest path for which there is only one given source S and there is only one given destination, say D. So, of course, by reversing the direction of this D and S of each graph, we can reduce this problem always to a single source problem. So, we want to work with single source, single destination shortest path problem. And now, the single pair shortest path. You are having the given initial vertex S and final vertex T. Our aim is to find out the shortest path from S to T. If we can solve the single source shortest path problem with source vertex S, then we can solve this problem too, obviously, because if we are starting from an initial vertex and we are moving to the destination, then we can also solve the shortest path problem. And it has another property, that is all pair shortest path problem. In the shortest path problem, not only we want to find out the shortest path between source and destination, basically we are trying to solve the shortest path between any two vertex. Whenever we are completing the shortest path algorithm, we can develop the shortest path among the source and the destination, as well as the shortest path between any two vertices. Please note this one, shortest path between any two vertices, which actually we have not done using the CPM method or the path method. So, some notations which I will use actually in the development of the algorithm. The first one is the predecessor vertex pi of V, predecessor vertex pi of V. Predecessor vertex pi of V is in the search procedure. If we can find a path from U to V with minimum weight, that is, you are moving from vertex U to V with a minimum weight during the shortest path algorithm, then you say that U is the predecessor of V. Or in other sense, if you see, if this is your U, if this is your V, there is an shortest path between U to V, then we say that there is one predecessor, U is the predecessor of V, or in other sense you can say predecessor is nothing but the parent, that is, U is the parent of V. So, basically this pi array tells you what are the predecessors of different vertex. For a vertex, what is the corresponding predecessor, that is being written on this pi array, and this predecessor is always has to be uniquely defined. And there may be a case where V is a source vertex. So, if a source vertex is there, the predecessor of the source vertex is always nil. That is, if this is the source vertex say S, then pi of S, this is equals to nu. So, for the source vertex it is always nil, otherwise you are getting, if from U to V there is a shortest path, then the predecessor of U is V. We say that the predecessor U is the predecessor of V. This is one notation. The other notation is the distance function. For a specific vertex S as source, the distance from S to vertex B is computed algorithmically and we denote it by dV. So, the distance we denote it by dV. So, the distance is between, if you have the source S, if you have the destination D, these two are there, you have a source, you have a destination. So, what is the distance between S and D, that is basically stored in this dV. So, basically dV denotes your number of edges it requires to come to the vertex B from source S, and also it is known as the shortest path estimate, that is from move from S to V, what is the shortest path, that also we write over here. Now, there is a famous algorithm which we call as Dijkstra algorithm. This Dijkstra algorithm is used, we will basically discuss this Dijkstra algorithm to find out the solution of to find out the shortest path. This algorithm can be applied for the problems where edge of the graph has non-negative weights, number 1. For non-negative weights, the Bellman-Ford algorithm is also available, although we will work with the non-negative weights and we will discuss only the Dijkstra algorithm, because due to shortage of time we cannot discuss you both the cases, that is weighted case and non-weighted case we cannot discuss. If you see, the Dijkstra algorithm is based on only two things. One is you initializing the single source and another one is you are relaxing. So, we have to know what do you mean by we are initializing the source and what do you mean by we are relaxing. So, what is initializing source? Initializing single source GS. If you see what we have written, for each vertex V belongs to VG, you take anything. This is the initialization single source graph. For that reason, if you see we have written capital G comma S, that is it has a single source. For each vertex V, what you will do? You will make the distance vertex V equals infinity, and your pi V. What is your pi V? If you remember, we have told in the just this one initialization. For initialization, we are using pi, whereas for the other one we are using the distance, we are using V. So, pi V, your dV is just your predecessor vector you are storing in pi, and whereas the distance vector you are storing in V. So, here what you are doing for the each vertex V belongs to VG, what you have to do? You have to make the d, that is dV equals infinity, you are making dV that is equals to infinity, and initially you are making this pi V, this is equals to nil, and pi V equals to nil. Whereas, if S is the source, then your ds value that will be equals to 0. To make it simple for you, suppose you have a graph like this, I am just drawing the graph very easy. We have a graph like this, the nodes we are defining as say O, A, B, C, and the distance suppose it is 5, 6, 7 and 8. So, basically what you are doing initially, the value is, if you see initially we are writing this value as vertex value as 0 over here, and all other vertex values will be infinity. This we call as the initialization. This you are making as 0, and all these elements, all these vertex values you are making as infinity. That we have written in the algorithm. If you see the algorithm over here, dV equals to infinity and your pi V is nil, whereas for the source ds equals to 0. And similarly, after initialization, your pi s, that is the predecessor of source, there will be nothing. So, predecessor of source always you will write down as nil. So, we have to note this one, that the distance of source is always 0 initially, and the predecessor of source is nil, whereas the distance of any other vertex we will initialize with infinity, and your the predecessor of each of them will be equals to nil, because we have not evaluated that. The next one is the other procedure, that is the relaxing procedure. For relaxing an edge u to v, we have to test whether you can improve the shortest path whatever we have found for that one or not. Whatever shortest path we have found, that is correct or not. So, if there is a already you have obtained a path from u to v, that is, if you see in this figure, suppose I have derived a path like this. Let me denote it by this red color pen. This is a path. So, I have to basically there is a path, and if you see the distance will be 5 plus 6 11. Can I find out any other alternative path by which the distance will be less? And that actually we find out by this relaxing method. The basic idea is this one. So, in the relaxing method, what we are doing here, if we are trying to, we can improve the shortest path from u to v. So, that by going through v, by improving, if improvement is possible, then you have to update the value of dv and pi v, and relaxing maybe it may decrease the value of dv and update pi v. This is basically done by this small algorithm. If you see the relax UVW, this is the algorithm. If dV is greater than du plus w uv, then dV will be equals to the smaller value, that is du plus w uv, and your pi v will be equals to. So, let me just write down what I am saying, that is, if dV it is greater than du plus wuv. If this is true, in that case what you will do? You will replace dV by the smaller value du plus wuv. So, what does it actually means? The meaning is, again I am just drawing these two paths, 3, 4 paths. This is the initial value. Suppose this value is 10, this value is 5, this value is 12, from here this value is 7, say. Some links are there, I am not going to these links. What I want to say, your d of v is this value 10. By some path, can I get some value such that if you add with this, whether the value is less than this or not. If it is less than this one, in that case your dV will be replaced by du plus wuv. So, this again I will explain with an example. So, this is the first one, relaxing one, and algorithms for finding out the shortest path will initialize the source and then relax each edge either once or more. That means, by relaxing you can initializing single source and you can relax each edge with once or more. That is, you can reduce the value of each edge more than once also. And in Bellman's algorithm, in Dijkstra algorithm you are relaxing only once, whereas in Bellman's algorithm you can relax it several times. This is the basic difference between the Dijkstra algorithm and the Bellman-Ford algorithm. Next, if you see, the next is the Dijkstra algorithm solves this single source shortest path problem as on weighted G equals V e for the cases in which all edges are weighted and they are non-negative, that is W of u v greater than equals 0. And Dijkstra maintains a set of set S of vertices whose final shortest path weights from a source to a source S have already been determined. That is, we are having dV equals comma S of V. This already we are doing. What is the basic structure of the Dijkstra algorithm? You are given a graph G equals V of E. S is the set of vertices whose shortest path you want to find out, and V to S are the remaining V minus S. V is the all the vertices, S is the set of vertices whose shortest path we will be finding, V minus S obviously will be the remaining number of vertices. Your D, as we have told, basically it is the small d array of best estimate of shortest path of each vertex. This is small d, not capital D, and pi, this is the array of predecessor of each vertex which we have defined earlier. So, initially what you are doing, I have given 1, 2, 3 like this. You have to initialize your the distance and the predecessor, that is you are finding what is initialized D and predecessor. Then the set S which contains all the elements, that is initially empty. While there is some still vertices in V minus S, you have to sort vertices V minus S according to current best estimate of their distance from the source. That is, whatever remaining vertices are there, what is the minimum distance that you have to find out. Then you have to add u, the closest vertex in V minus S to x, and we will relax the all the vertices, still V minus S is connected to u. The basic property what we are using, basically one is we are trying to find out two things. One is the optimal subpath and another one is the triangular inequality. This are the basic principle is used. Your subpath of a shortest path is itself a shortest path. This is the basic principle. Any subpath you take of a shortest path, always that must be the shortest path. And the if you are having a smallest length between u and v, then always you take any other 2 points, that will always remain the shortest, and this we call as the triangular inequality. Now, the Dijkstra algorithm I have just written in terms of the algorithm here, which we have written Dijkstra G comma S, that is a single source. Initial line, if you see, you are making d s, that is equals 0, actually that is not properly visible. If you see d s, this you are making initially 0. Next is for all v belongs to v minus s, you are making d v is you are making as infinity, pi v equals nil, and your s is approaching 0, s is null. These three things, that is if you see the slide, for all v do d v equals infinity, pi v equals nil, and your s is 0, s is null, and your q is v. These two are important, I will discuss. Please go to the slide here. So, these three parts, do d v equals infinity, pi v equals nil, this part basically you are doing as the initialization. As we discussed, it has two basic parts, one is the initialization and another one is the one is initialization and another one is the relaxing. So, the first part we have done, that is the this one. What is S? S is the set of vertices, set of visited vertices. Please note this one, set of visited vertices. How many vertices already we have visited? And obviously, this will be initially empty because we have not visited anything. So, S is the number of visited vertices, and your Q, initially it contains all the vertices. Initially Q is all vertices, and so what I will do basically, initially S is empty, your Q is all the vertices. Once I am visiting this vertex, then that will be moved to S and that will be deleted from this. And ultimately, our aim is we will repeat our process, relaxing process, until your Q is not equals phi. For this condition, we will move from there. So, let us see. So, the next part is while Q not equals phi, in the slide if you see, the next one is while Q not equals phi, do u equals minimum distance of q comma d, that is you have to calculate what is the minimum distance. Then if du equals infinity will break, otherwise S equals S union u, and then for all v vertices belongs to neighbors of u, do if dv greater than du plus wu, then dv will be du plus w u v and phi v equals u. Again this part if you see, the last part is basically the relaxing part. So, it is consisting basically of two parts, one is the initialization part, another one is the relaxing part. In the initialization part, you are initializing two things, one is the distance array and another one is the predecessor array, and then in the relaxing part you are revisiting all the vertices, and if possible you are trying to reduce the cost, and so these two together will give you the shortest path. Now, let us take one example and see how it works. So, let us take this example. In the following graph, if you see, we are having S, and from there you want to visit the single source problem. This is not the single destination problem, of course, because you may visit to any vertices, but the source is same. So, it is, if you see from the graph, it is a directed graph, number 1. Number 2 is it is 1, after directed graph it is also weighted graph, weights are given. So, let us see what happens in the next steps. Let us see here. So, step 1 is your initialization problem. Step 1 is the initialization. In the initially what is happening? You are having these things. The graph, if you see the graph I have drawn over here, whatever graph problem was there, that is S to u, u to v, like this way, all the weights are also given over here, like 100, 10, 30, 20, like this. Now, let us see the problem. In the problem itself, you are having the initialization problem, that is S to u, u to v. What I have told you, we have to find out what is your d. First, what is the distance and what is your pi. So, your distance, obviously it will be S is 0, as I told you, since it is source, and for u all are infinity. This is the basic thing. in the initialization process, the distance of all vertex will be infinite and distance of S is 0. Whereas, whenever you are calculating your pi, we have not written source over here, because for source nothing is coming, source is already here, and for all others the predecessors obviously of u, v and all these are nil. The predecessors of this one are nil. So, once I have written this, I have to calculate this matrix. Once I have calculated this matrix, then this distance values you put it here. Distance of source S is 0, you write down here 0. Distance and all others basically they are infinity, infinity, x is this and this is infinity. So, you are I have written it red, so that you can understand it properly. So, you are calculating first what is the distance array. From the distance array on each vertex you are writing now the values. For the initialization, you know source of the distance is 0, whereas source of other vertices is infinity, and you have written all this. Whereas, for the predecessor, for all of them predecessor initially is nil. So, initially your S is phi and your Q is all the vertices, that is S, U, V, X and Y. I think the first step is clear, that your S is phi and your Q is S, U, V, X and Y. Now, let us come to the step 2. For the step 2, basically again you are having this thing. You are having this one, you have to first calculate what is the distance, what is the pi, and then from there you will calculate the this one. So, for calculation of this, what is your mu say? I am just writing mu. What is your mu? Mu is the minimum distance of Q. That is, what do you mean by minimum distance of Q? Minimum distance of Q means I want to say which vertex is having lowest value over here. You see the earlier one graph, in this vertex you have supplied the values, which vertex is having the lowest value. Obviously, the source will have the lowest value, the source value is 0. So, therefore, your mu is here, since the source value if you see it is 0, this is the minimum value. Therefore, your mu is actually it is S, and your capital S basically now it will become S. I will write down that your capital S is basically S. So, once I have obtained what is the distance, now from this neighbor what is mu, you are calculating which are having the lowest value of the vertex, that vertex you choose. Now, from that vertex you find out what the neighbors of these vertexes. Who are the neighbors of these vertexes? The neighbors of this vertex, one neighbor is u, another neighbor is x. Neighbor means there is a directed graph from S to u or S to v, not the opposite way. If there is a direction from S to u, you are telling that u is neighbor. So, neighbor of S is u and the neighbor of S is x. So, now what I have to do? I have to find out the distance of u and the distance of x. What is the distance of u? Distance of u is the value of the vertex S plus this weight whatever you have given, value of this plus the weight from moving from S to u. Therefore, your SU, if you see du, that is distance of u, basically it will be the value of the source S, value of the vertex S, that is 0 plus weight for moving from S to u, that is 100. So, you can write down from here that your du is equals to 0 plus 100. So, this is equals to 100, and on the same way I have to calculate what is dx. What will be dx? Dx is what was your predecessor, predecessor is S. What is the value of the vertex S? Vertex S is 0 plus the weight of this path S to x, that is 50. Therefore, dx will be equals to 0 plus 50, and that is equals 50. So, you can write down d of x, that is equals 0 plus 50. So, this is equals 50. So, now you got a change over here. The value of du, the distance of u, the distance of x are not now infinite. So, it is now fixed. So, now what are the values? Let me write down over here. So, for this let me just calculate first the distance is what from S to S, it is 0 obviously. For distance of u is now 100, just now you calculated. Distance of x, that is equals to distance of x is 50, v is infinite and y is infinite. What about the predecessor? Predecessor, who is the predecessor of u now? Predecessor of u is x, predecessor of x is s. Predecessor of u is x, predecessor of x is s. So, change it. Predecessor of u is s, predecessor of x is s, for v and y it is nil. So, once you have drawn this, your s is this thing. So, from q what will happen? Earlier your q was s u v x y. Now, already you have visited s and that has come to capital S. Therefore, you should delete this s from q. So, that now you will get q equals u v x and y. So, once I have written this, now write down the distances. For this it is 0 still, for the next one it is 100, for this one it is 50 and for this is it is infinite and for this it is infinite still. Now, whenever, so like this way, first you are calculating the distance. No, first you are finding out whatever vertex are there, which are as the minimum value. The minimum value obviously is 0 among all these vertex values. So, you are finding what is the neighbor of this vertex. After you finding the neighbors, you are finding the distance of those neighbors using this formula, that is value of that vertex plus the weight for going to from vertex S to u, like that. So, once I have done this, you are filling up the array D, distance array, you are filling up the predecessor array. For u, from that figure it is clear, predecessor of u is S, predecessor of x is S, we have written it. Accordingly, the set capital S and capital Q you are updating over there, and then you are writing the distances over there. If you see, once I have obtained this from S to u, this is the shortest path. This sub path is the shortest path for moving from S to u. You cannot minimize this distance value 100 in any way. If I want to move from S to u in by any means, I cannot minimize or I cannot make it lesser than 100. So, therefore, what I am doing? I am putting an array over here. Similarly, to move from S to x, this subpath also gives you the minimum distance, you cannot minimize further. So, the subpaths which I will not be able to minimize, that initially I am putting by this red arrow. So, this is your step 2. Now, let us go to the step 3 now. In step 3, again you are having now in step 3, what I have to do first? This was the figure for the step 2. So, from this figure, first I have to find out which vertex is having minimum. Now, from which vertex you will check? You will check from only the vertex u, v, x and y. You do not have the vertex s now. So, basically I will go through the vertex whatever is there in the set Q, because after each step for the vertex it will be one vertex will be removed. So, among the vertex u, v, x and y, if you see the vertex x has the minimum value, that is 50, the vertex s has the minimum value. What are the neighbors? The neighbor is, one is u, this arrow is there, one arrow is to their v, another arrow is there y. So, from this remaining vertex u, v, x, y, we are finding minimum distance is there for the vertex x, that is 50, and the adjacent vertex of x are u, v and y. What is the distance now we have to calculate? The distance, say du, if you see, what will be du now? Du will be the distance of the vertex x plus this one, that is du will be equals to your du, this is equals to, I am just showing one, you can calculate afterwards. Du will be vertex this plus du initially this is 100, initial value is 100 if you see, and what is the distance now? 50 plus 30. So, 50 plus 30 this is equals 80. So, 100 is greater than this. So, therefore, I have to now update this du from 100 to 50 plus 30 80. What about dv? Your dv will be dv, if you calculate 50 plus 90 140, your dv will be 50 plus 90, that is equals to 140. Similarly, your dy, this will be dy will be 50 plus 20 70, this also will be replaced, because in both cases alpha are greater than. So, what are the distances you are getting? From S to S it is 0, from u now, earlier if you see it was 100, now it is replaced by 80, from V it is 140 we have calculated, from x it remains fixed, that is 50, and for y it is 70. For y if you see it is 70. Similarly, for now you see the what are the predecessors. For u the predecessor is, now it is not the 80 is there, 80 coming from through this part. So, the predecessor of u has changed now x. Similarly, for v also the predecessor is x, for x the predecessor is obviously x, and for y also the predecessor is x. So, if you now write down the values, now it is 0, it is 80, this one is 50, this one is 140, and the last one is 70. So, now the if you see the arrows will be changing, this is the minimum value. To move from here to here, I will not go to this direction. If you go to this direction, the value is 100, whereas if you move from this to this, the distance is 80. So, one path will be this. To go to this path, 50 plus 90 140, and then the 50 plus 20 70. So, this is the S to u. So, basically whenever you are moving the steps, the shortest path is being changing, which we are showing by the arrows over here. Now, come to the same way, if you calculate for the step 4 now. For the step 4, if you see over here, sorry, I have not written your minimum of S, your S is here S and x, whereas q is u, v and y. So, now basically you will check between u, v and y what is the minimum one. The minimum value is here your y, and for y if you see the vertexes S and v, these are the neighbors. So, you will calculate ds and dv. Your ds is equals to, I am just writing from here, ds initially is 0 and this is less than 70 plus 70. So, basically there will be no change, whereas your dv this was 140, dv is 140, and what is dy? dy is your 70 plus 60. So, 70 plus 60. So, 140 is greater than this. So, your dv will be changed, your dv will be changed. So, v distance now will become 130. All other distances will remain as it is, that is 0, 80, x is 50, y is 70. For u it is again, if you see it is x. For v now it has changed to y, for x again it is s, and for y it is, for y the earlier one, that is x. So, your s now will be s, x and y will be removed, and because the you are taking y was the initial value, minimum value. So, q is u v. So, the values will become now, this is 80 remains fixed, this is 50, this is 70, and this one is 1, 3 and 0. So, this value has reduced. So, this path will remain as it is, whereas the path, this path was there, if you see, if you move from this to this, the distance was 140, now distance is 130. So, now this sub path is not the shortest one. So, I have to write down the new shortest path will become 20, and this is 70 and 60, that is 130. So, this arrow actually will be on this direction, this is on this direction. So, this is this, basically I wrongly wrote. So, this is 70 plus 60, that is equals to 130. So, this is the shortest path over here. Now, let us go to the step 5. In step 5, what happens? If you see in step 5, what happens? You are having here only u and v. So, between u and v, which one is the minimum? Obviously, again u is the minimum 80 and 130, and who is the adjacent? Adjacent of u and v, one is u is x, another one is v. And if you see adjacent of u is v, that value will be mod. So, it will not be, it will x will remain unchanged over here, because you are not able to reduce it. This is mod 80 plus 30, whereas for this case, if you see this 130, your dV, what is your dV now? dV initially, if you see, your dV is 130, but if you calculate, this will be distance is 80 plus 10, that is 90. So, 80 plus 10, which is greater than this. So, this distance 80 plus 10, this is 90. So, if I travel from here to here, then my distance will be less. So, this 130 has to be changed. So, since in that case your value of distance of v will be changing to 90, and all other values will remain as it is, that is 0, 80, 50 and 70. Whereas, for u it is x, for v it is now u, for x it is x, for y it is x. So, if you see, your s will now become s, x, y and u, your q is v. What is the value over here then? It is 0, it is 80, this is 50, this is 70, this is 90. So, now the arrow will be, one is 50 plus 30, 80 plus 10, 90 to move on this direction, and you can move on this direction also. So, 20, and now sorry, if you move from here to here, it is 50 plus 20, this subpath is shortest, but now this subpath is not shortest, because this subpath was having 130 distance, 70 plus 60. So, this is not a shortest path now. So, earlier someone may be shortest path, now it may not be the shortest path. So, now this is the figure over here. This in the step 7, what is happening here? In step 7 now, if you see, you are having only one case, that is only v is remaining. So, what is the neighbor of v? Neighbor of v is only y, and in that case the value will be, if you see over here itself, it is in that case 90 plus 40, 90 plus 40, 130, which is greater than 70. So, this 70 will remain unchanged, or in other sense, in step 6, there is no change. We can say that in step 6 there is no change. So, since there is no change over here in step 6, because in step 6 there was adjacent was only mu equals v, only one vertex was there, adjacent was y, and the cost was more 90 plus 40. So, there will be no change. So, this is the final graph, because now your q, in this case your s will be, now in step 6 your s will be x, y, u, and your q will be equals to null. So, we are stopping the algorithm now. Once we are stopping the algorithm, so now you can say from here what will be the path. I will say it, I will write it S, that is the source. From u, if you want to move, from S to u, then what will be the path? S to x, x to u. I am writing this S to u, u to x. What is the distance or cost? Your distance is 80, it is written over here. So, your distance is 80. If you consider v, I want to move to v. If I want to move to v, then s to x, s to x, x to u, u to v, and the distance is 90. So, if you want to move from here, then s to x, x to u and u to v, and this value will be d equals 90. I have written this one wrongly, this would be x to x and x to u, because s to x and x to u. For u, s to x and x to u, for v, s to x, x to u, u to v, minimum distance is 90. For x, if I want to move, there is only one case, that is s to x, and the distance is 50. So, distance is 50, and for the y, if you see, if I want to move to y, s to x, x to y, and the minimum value is 70. So, I am moving from s to x, x to y, and your d is equals to 70. So, like this way, if I want what is the minimum path, then shortest path, the shortest path is s to u, shortest path is s to x, x to u, and u to v. This is your shortest path, s to x, x to u, u to v, this will be the shortest path. So, the beauty of this algorithm is that not only you are finding out the shortest path from the end vertex, but you can find out any shortest subpath if you want to move from one vertex to another vertex. Suppose I want to move from x to v, then in that case the path may be s to u, u to v, like this way. And there is another problem which you can solve of your own also on the same way. The only difference is it is undirected graph. If you see the graph is undirected graph, that means there may be, I may go from O to A, or I may go from A to O also. You can solve it of your own. Thank you.